Hello everyone, my name is Tigan Hushtaran and this is my walkthrough for assignment 3. So I'm starting part A, convolution or on a 2D image before we move to part B in the neural network. So here I input NumPy, PIL, matplotlib and request so I can load an image into an array and plot results. These are the tools for manual convolution in the next cells. So I downloaded the car image for URL, read the bytes with PIL and convert it to a NumPy array. So each pixel is a number. So I display the image, check the array shape and whether the color channels match. Then keep one channel, so I'm working with grayscale to the array for convolution. Okay, so I pad the image with 0, so 3 by 3 kernel can reach the borders, use a simple identity style kernel loop over every position, multiply the patch by the kernel, sum and fill the output array, then plot it in gray. That's the basic slide and multiply idea for convolution. So I define squash pixel value to clamp results to 0 through 255 and conv to d kernel to pad. Slide any 3 by 3 kernel and optionally squash so the next demos reuse the same function. Okay, so this cell uses a horizontal line kernel, strong weights on the middle row and negatives above the above and below. After conv2 kernel, I plot the response in grayscale. So next are my answers for questions 1A and 1B, two different diagonal line detectors. So for the 1A, based on the kernels represented on the above image, create a kernel to detect 45-degree lines using convolution applied to the cars image and plot the result. And 1B, so I built a 3 by 3 kernel, weighted long one diagonal uh, convoluted with the car image using a conv2d kernel and plotted the result with a title so you can see 45 degree structure. And for 1b, based on the kernels represented on the above image, create a kernel to detect 135-degree lines using convolution applied to the car's image and plot the result. For 1b, I used the complementary diagonal kernel for about 135 degrees, ran the same convolution and plotted it next to compare with 1a. So this section applies three edge detection kernels from the assignment. Um, for question, for question 2, I apply each kernel with conv2d kernel and show the grayscale output for 2a, 2b, and 2c. So for 2a, kernel 2a uses this pattern convolution, highlights edges according to these weights, and here is the plot. So for 2b is the Laplacian style mask with a negative center and positive neighbors. So the plot shows where intensity changes. Okay, for 2C, kernel 2C has a strong center and negative ring. The output emphasizes edges differently from 2B, as you can see. Okay, now let's move to part B. Part B is CIFAR 10 and CNN. Data preparation, a baseline model, training curves, then deeper layers and dropout. So now let's import libraries. Okay, I load CIFAR 10, one hot encode the 10 classes, cast images to float 32 and divide by 255. So inputs are between zeros and 1. Okay, building the neural network model. The baseline sequential model has one conv2d layer with 32 filters and same padding. ReLU, max pooling, flatten, a dense layer of 128, and softmax for 10 classes. I compile with Atom and categorical cross entropy, call summary to show layers shapes, then train in the next section. So custom callback class for logging. This callback prints training and validation accuracy every 5 epochs, so I can monitor progress during long runs. I train for 50 epochs with validation on the test set and the callback. This produces the history used in the accuracy plots. So I train for 50 epochs with validation on the test set and the callback. This produces the history used in the accuracy plot. So here I plot training accuracy in blue and validation accuracy in red. Dashed. I'll refer back to this for overfitting in question 3 and I'll show new plots after the deeper model and after dropout. So the next headings uh, are my answers. So for question 3, did the network present signs of overfitting? If so, in which epochs? Yes, there are usually signs of overfitting where training accuracy keeps rising, but validation accuracy flattens or drops. In my run, that shows around epoch. Question 4, write down how many layers this model has and identity data types. So the original baseline has 5 layers, conv2d, max pooling, 2d flat and dense with 128 units, and dense with softmax for 10 outputs. So question 5, briefly explain what is the purpose of each of those layers. Um, conv2d learns local patterns, pulling down samples, flatten feeds the classifier, the hidden dense combines features, the final dense outputs class probabilities. So question 6, add one or more convolution layers to your model and run it again. So for question 6, I passed a deeper sequential model with a second conv2d block, 64 filters, and a second max pool. Then I run compile, fit, and plot again to compare with the baseline. So question. So now let's move to question 7. Compare the results between uh, original model made using Keras sequential versus the bigger model with at least one extra layer added. To describe what are the difference between them. So compared to the original, the deeper model had um, higher peak validation accuracy and widened train validation gap based on the two accuracy plots. So for question 8, I added dropout after flatten on the deeper model, trained and plotted again to compare with deeper model without dropout. For um, question 9, dropout randomly zeros some excavations during training, so the network cannot depend on the same units every time at test time itself. That reduces overfitting and often help validation accuracy.